Hi, Bill Vales here. I'm here today with Tom Vales, also known as Dr. Electricity, and Tom's going to show us that science, and in particular electricity, can be fun and entertaining. We've done a number of these shows, and each show there's something new to learn. Tom is on staff at Suffolk University in Boston. And Tom, what do you do there at Suffolk?
Laboratory coordinator for the electrical engineering department. I take care of all the labs, I teach labs, help students with projects, do a variety of things, really.
Okay. And some of your teaching involves these devices?
Yes.
Okay.
Yes.
Okay, so, so there's some really neat devices here. But first, a question or two. What's electricity?
Simply put, electricity is a flow of electrons through a conductor.
Okay. So electrons, so now I have to ask, what's an electron?
It's a subatomic particle. It orbits the nucleus of an atom. All atoms have electrons.
Okay. Okay, so the picture I have in my mind is an atom has protons and neutrons in the center. Okay. Yep. And we have electrons flowing.
That's right.
Spinning around them. So that's the electron. Okay. And how fast do those electrons move?
They can move in a vacuum to the speed of light, or they can 186,000 miles per second, or in a conductor about 2 centimeters per second.
Wow, what a difference in speed.
Yeah, it is. It is. Yep.
Okay. Okay. All right. Some neat toys here. Let's start us off here. What do we have here?
Okay, this is a little item called a ring launcher, and that's exactly what it does. You take a metal ring, has to be a conductive ring, and you drop.
So by conductive, you mean?
It will pass current.
Okay.
And it's dropped over the core of this coil. You notice that there's a bunch of rods that make up the core. That works extremely much better than a solid piece. Okay, these little pieces work a lot better.
Okay. Okay. All right.
And I have an old camera flash here. Just some junk flash I picked up, and it's been modified. And the modification is this. I disconnected the flash tube and instead ran these 2 wires from where the flash tube would be connected out here. So what this is doing is, and this is how you take a picture, it charges up a capacitor. Now, a capacitor is an electronic component that stores charge. That's one of its main duties. And normally when this is operating, the capacitor will be charged up, and when the little light comes on, it tells you, okay, we're ready to shoot the picture. Then when you press the shutter, the capacitor's energy is dumped into the strobe tube, and you get that brilliant white flash. Well, in this case, we're not dumping it into a strobe tube. We're dumping it into this coil down here that's around the core.
So this coil here, what is this wound with?
It's wound with an old style wire that you don't see much of anymore. It's called cotton covered wire.
Okay, cotton covered.
Covered wire.
And what's the cotton covering?
It's covering either bare copper, or it can cover shellac copper, but for the most part, it's covering.
Okay. Okay, so that's a copper coil there.
Yep.
And you have a core here.
Yep.
Okay. And this core is not solid.
No, it's many pieces.
Many pieces. And can I touch this without?
Yeah, no, don't worry about it. Don't worry about it.
I do worry.
Well, I worry about it.
Okay, so there's a ring there.
Yep.
And this ring is made out of what?
Aluminum.
Aluminum. Okay. So we're going to place that on.
Now, the last piece of this is something I'll bet few of our viewers have ever seen. What you see in here, you can see a silvery metal.
Oh, look at that.
That's mercury. This is called a Mercury Switch, and HG, and it's has a lot of uses in furnaces, temperature control stuff, ovens, light switches on the wall. When they first came out with Mercury switches, they were silent. There was no more click, click. Well, we've gone wacko about mercury and just about cleaned up every bit of it we can. It's like anything else. You just beware and treat it accordingly. Anyway, the mercury is used in here so that I can switch the energy from the capacitor into the coil, and there's so much energy that if I used a regular switch and clicked it, it would only last for a few clicks before it would weld itself together.
Okay. Okay, so this is called a ring launcher.
Yep.
Which means we're going to launch some rings.
But
Okay.
I should tell the viewers what the principle is here. That's the key item.
I want to see the rings launched.
All right, well, we'll launch that and then explain it.
Okay.
Ready?
That ring launched a good 12, 15 feet in the air.
All right. I'll try one more.
This is a narrower ring.
Yeah.
The other ring is out of reach, and we're going to launch this. That's over there.
Yep. Now, here's something
Okay.
we're going to do.
So
If
now,
I could get a close-up of what I'm holding in my hand. This ring has a slot cut in it.
okay, where the other rings were solid.
Yep. So this has
Solid.
got a cut in it. If you can see that. So we're going to put it on here.
Can I launch this one?
Sure. Let her go.
Okay. That figures I get a dud. Okay.
I can
So-
explain why that happened.
Yep.
All right. Let's shut
Okay.
this off. So question is, why does the one with the slot not launch versus the other ones? Well, there is a law in electricity called Lenz Law, L-E-N-Z. It's one of those basic laws that define a whole line of reasoning and research, okay? And what it is this. When the energy for this capacitor is dumped into that coil, what it does is it makes a magnetic field.
Okay.
Now, the ring that's on there gets current induced in it, and that has its own magnetic field, and that works into opposition to the one driving the whole thing, and that just throws it off.
So this is repelling.
Yeah,
Okay, so when I put the current on this,
yeah.
I almost caught that. What was this made out of? Because this didn't go
Oh,
nearly
no,
as
no,
high.
no, it didn't because I shut it off, and you were just using what residual power
Oh,
was in there, that's all.
okay.
The reason why the ring with the slot didn't launch is because it's an open circuit.
Open circuit.
You can't get an electric current in it, no current, no magnetic field. That's the thing about an electric current, that if you have electrons flowing in a wire or whatever, you get a rotating magnetic field. And if there's no field, there's no current, and vice versa.
No current, no field.
Yeah, that's just another one of these basic tenets.
So if we were to have put a wood ring
Yep.
on here, nothing would happen.
Nope.
Because that's not a conductor.
Right.
Now, we were using before aluminum,
Yep.
I think you said, but you have a copper ring here.
Yeah.
So what can we expect to be different with
Well-
aluminum versus copper?
You know, I would tend to say maybe at the size that copper ring is, it might be close to the aluminum,
Yeah.
but maybe not.
Yeah. But in general, copper's a better conductor.
Oh, yes, oh, yes.
Okay,
Yeah.
okay.
Why, do you want to launch a ring?
All right,
You
I'll launch
want to
one.
play with this thing, all right.
Okay, I'm going to launch one.
Yeah, you got to wait for the,
All right. All right. All right. Does this have a battery in it? This must have a battery in it.
yeah, it has 4 AA batteries.
Okay, so the battery are what is charging
Yeah.
the capacitor. Okay, we ready to go? Oh yeah, the light's on. Ready to
Lights
go.
on.
That's because I always listen. Here we go.
Wow,
Wow, that was close.
that was,
Okay. Ring launcher. What a,
this is a
what a
neat,
neat tool.
it is a neat project.
device.
I have some students that want to build one of these. I also witnessed a friend of mine's design that was putting rings up 150 to 200 feet.
I believe it. I believe it. Now, I have to ask one question. Why can't the batteries power this directly? Why does the charge have to be put into the capacitor
Because
first?
you need an extremely large amount of charge.
Oh, so the capacitor can charge up more?
Oh, yeah.
Got it.
A capacitor can charge up power over time,
Okay.
but when you want the capacitor to give you energy, it's more than happy to dump all its charge as fast as it can.
I see. Okay.
But that was a nice little gizmo. It's a nice demonstration tool.
Okay. When were these things built? Were these?
Oh, that experiment, those things are probably going back to the 1800s.
Okay.
I'm sure people were doing.
All right. What do we have here, Dr. Frankenstein? We seem to have a lot of wires and
Okay.
batteries and what
To
do we
give
have?
you a little background on this, this glass tube you see in here, and I'm holding another one here.
Extremely ornate.
Yeah.
Very ornate.
Extremely ornate. These are called Geissler tubes, and they're named after the man who brought them into existence, Heinrich Geissler. Now, he was a scientist, he was a glass blower, he was an innovator, and he had made a better vacuum pump so that scientists could study the effects of gases and so on liquids, solids, and so forth, using better vacuum techniques. Well, Geissler tubes caught on, and pretty soon every supply house had glass blowers making these things. They could be up to a couple feet long. They could have fluorescent fluids in them. They could have seashells in them, rocks. Some are beautifully ornate, but they're wicked fragile.
Okay.
But those were Geissler tubes. Now, somebody said, I wonder what a Geissler tube would look like if we rotated it. So this device right here that you see is called a Geissler tube rotator. It has a setup here in the front where I have some movable ends to accommodate different size Geissler tubes. This is the motor back here, and this is a exact copy of an antique. A friend of mine loaned it to me, and I actually made 2 of them. I made one for me and one for him, and as thanks for letting me use it. I've wanted to get one for a
you
long.
made this?
Yep, made it all.
Okay.
There's one thing I've always wanted, but when you see these things on eBay, they're going like upwards of $800.
So normally the Geissler tube, when it was first made, it had various gases in them.
Yeah, they
and
tried
material.
different stuff, yeah.
And they were sitting stationary.
Yep,
And current was passed
Yep.
through them
yep,
to show beautiful colors.
yep.
Okay. Now, about when were these first made?
Probably late 1800s.
Okay, okay. So, give us a spin.
So first, I'll light up the Geissler tube so you can see what it looks like
Yeah.
stationary. It's
Great.
got two different colors of glass here. What is charging this up is this device here. This is called an induction coil. It produces a high DC voltage sufficient to light up tubes like this running off of batteries. This was a common tool in laboratories for high voltage.
I mean, just to point out the workmanship just on this induction coil, you
Yeah.
said? Dovetailed, finger-jointed.
Yeah,
Lens,
it's unbelievable. Heavy brass hardware.
Beautifully done.
Yep, so let's
Okay,
see if we
here we
can
go.
light the light up. Okay, so you can see, oh, let's do this. Yeah. Okay, so you can see something going on there.
Okay, so you're passing a current through there.
Yep.
And what type of gas is in there?
Probably just atmospheric. I mean, just maybe a little bit of argon.
Okay, in a vacuum?
Yeah.
Okay, so, got it, argon.
All right, so now we'll make it spin.
Okay.
And this was just somebody's idea. It's kind of a whimsical thing, again, but a lot of people made them. Now there goes the tube.
Wow. Wow, neat. Look at that.
And you can,
So there's a lot of different bits of science going here.
Oh,
Your motor, elements, spinning around in the glass tube,
high voltage,
high voltage.
vacuum technology, and you can see there that
Yeah.
that's what,
So this is DC. This is being powered by DC.
right,
Okay, okay.
yep,
Okay,
all
well-
direct current.
Okay, so, you know, these devices, they're just aesthetically pleasing to look at.
Yep.
They're
Yeah,
works
yeah,
of
they
art.
do.
okay. What do we have here?
This is a small Tesla coil that I built, 7, maybe more years ago. We had a Who Can Build the Smallest Tesla Coil contest in our group, and this was my entry. And I just had a lot of fun doing this because this was a great example of packaging. And if there's anybody out there in the audience and works in a mechanical engineer or having to put things into a system and get them all to fit, they know what packaging is. And this just worked out, I feel, really well. Nikola Tesla, who was the inventor of the Tesla coil, was the gentleman behind the electrifying of Niagara Falls. He, with George Westinghouse, was responsible for getting that up and going. It's still in use today. And Tesla made, he made all sorts of things. He had over 700 US patents.
Wow.
Now I'm not saying Thomas Edison was stupid, but I'm going to say that Tesla eclipsed Edison with what he knew. And Tesla's invention of alternating current, that's what we all use today. It's something we're addicted to. Everybody, we use electricity.
So we think of Thomas Edison being associated with direct current, DC
Yep,
current.
yep.
And Nikola
Tesla.
associated with alternating current,
Yep.
AC current.
Yep.
Okay.
And
Okay.
Edison, till his dying day, would never admit that direct current was inferior to alternating current. Which, well,
But clearly, they both have their uses.
oh yeah, they do. They do direct
But I
current.
think when they tried to electrify cities with direct current, they quickly found the limitations.
Yep.
There were-
They had to keep building more generating plants.
Yep.
So Tesla's
And there were wires just
everywhere.
all over the place. Okay. So
So
Tesla
this
coil.
is
Now, I need to say, on a previous show, we had another Tesla coil you had.
Right.
That was wound around a bucket.
Yep.
Much larger.
Yeah.
And I've seen other Tesla coils of people that are in your circle that are huge.
Oh, yeah.
I mean, huge.
I have friends that have made coils that put out in excess of 20 feet of spark.
Yeah. Okay, so where should I stand?
Yeah, you're fine.
Yeah.
This is a nice demonstration device for a classroom.
Okay, so now what's this device here?
Okay, this is a variac, and what it is a variable transformer.
All right. I can smell a lot of ozone.
Yes.
Wow. A lot of ozone.
Yep.
What's that from?
That's from the electrical charge going through the air, and it takes the oxygen molecules and it bangs them around, and it comes up, instead of an O2 molecule, it comes up with an O3 minus.
Okay,
And
that's ozone.
Ozone is very beneficial in small quantities. It can be used as a sterilizer, air freshener, but in large quantities, if you inhale it, you can get nitrous acid in your lungs.
Okay.
And
So that current was beating up on some O2
oh yes,
molecules.
yep.
Molecules. Okay, so now you held up there that tube,
Yes,
and it showed yellow.
Right.
Why did that show yellow?
because that's the color of the phosphor that is on the tube,
Okay. How about the gas in the tube?
mercury vapor.
Mercury vapor. And again,
Mercury
that's in a
vapor,
vacuum.
yeah, and it ignites and it fluoresces, and it puts out ultraviolet light, and that's what causes that to,
Okay.
sort of like the same thing that happens in a fluorescent bulb.
Okay. So now what are you going
You want
to be?
to look at St. Elmo's fire?
St. Elmo's fire. Explain to people what St. Elmo's fire is.
St. Elmo's fire is a phenomenon that occurred on the masts, the ends of the masts of ships, the ends of the wings of airplanes, occasionally on the propellers of airplanes, and even on the heads of Chilean Indians in South America. What happens is this: you have a storm coming, an electrical storm. So the storm is moving in, and it's charged. It's got, you know, this is right before it wants to strike lightning. It has this incredible electrical charge. Well, if this cloud's coming by a ship out at sea, and the charge up there builds up, then what happens is, on the masts, that they start to emit charge in the form of electrons in purple flames, and that's St. Elmo's fire.
Now, is that like a lightning rod?
Not really,
Okay.
not really. But St. Elmo's fire was something that scared the living daylights out of sailors probably years ago.
Yeah. Well, I know it wouldn't do me well being on a plane observing St. Elmo's fire going around the wing.
I would have liked that.
Okay.
I'm going to see if we can pay attention to the end of the tube here, on the end of the wires. And you should be able to see St. Elmo's fire before it contacts the coil.
Can I smell the ozone?
That coil has never done that distance before.
Okay, well, let's...
I don't think it's gonna, let's try one other thing. Try this.
See, science requires experiment.
you'd be looking for a faint purple.
That goes around the...
No, that just would be coming out of the ends.
see.
But the light is too bright, and I can't see it when it starts.
Okay.
But
Well, fire it up once more. Let's, at least we enjoy the sparks. How many volts are we dealing
they
with?
say 75, I don't know, 150,000 perhaps.
150,000
Yeah, just volts.
Okay.
But that is open to debate because there's never been a clear-cut estimate of how much voltage does what length in spark. It has to do with temperature, humidity, whether you have needle point electrodes or round electrodes. But this guy here is a good teaching tool.
Now, the idea that an electrical current is being passed in the air effectively,
Yeah.
that seems like a pretty unique idea, that you can pass an electrical current without wires.
Oh yeah, that's true. But to pass it through the air requires a fairly good amount of voltage because of all the, you have electrons, but you have air molecules, and air molecules are, you know, much heavier. You can pass, like we just saw here, it just requires a fairly good charge.
Okay. Well, this has been very interesting again. I know there's no end to these devices and experiments. I want to thank you very much for
No problem.
Coming
no
here?
problem.
and tune in again, and we'll have some more electronic devices and fun with electricity with Dr. Electricity. Thank you.